Hello and welcome. This video we are going to be talking about projectile motion and the concepts and key points that go along with projectile motion. So to begin us out, as always, I want to start with the definition of what the concept is that we're dealing with. So for projectile motion, when we look at the definition of this is simply the motion of an object thrown or projected into the air and subject to only the acceleration due to gravity. Another term that you're going to need to know is that of projectile. And this is the object that is thrown or projected into the air. The path that it follows, that is its trajectory. One other term that you need to be familiar with is that of apex. And this is the maximum height achieved by that projectile. Okay? So now that we've got those definitions out of the way, we need to look at a couple of key points. The first of those is that acceleration due to gravity affects all objects equally, regardless of the mass of that object. So, for example, I've got this little foam cube, and I've got this book, and they have different masses, but if I take them from the same height and I allow them to fall, what we find is that they're going to strike this table at the same time, or approximately the same time. Okay? And that's because acceleration due to gravity doesn't depend on the mass of the object. Acceleration due to gravity is a constant at sea level, 9.8 meters per second squared. Now, as you move up from sea level, we do see that value decrease. As you move below sea level, we see it increase. So typically, we are going to stick with 9.8 meters per second squared for any type of problem that you're going to work in general physics, even AP physics. We use 9.8 meters per second squared. Okay? So the idea with this is that because acceleration due to gravity affects all objects equally, regardless of mass, we don't have to have a unique set of equations that are dependent on the mass of the object. Okay? So the other key point to this, though, is air resistance. If I take these from an extremely high position and I allow them to fall, what we will see is that the book has more air resistance than the cube because of surface area. So as a result, over a long distance, we'll see the cube hit the ground and then the book, because air resistance does not affect all objects equally. A better example of this that you've probably seen is if I take a book and then a feather, hold them at the same height, and I drop both of them, that book is going to fall, that feather is going to float downwards. And again, it's because that feather has a greater amount of air resistance. It's not that acceleration due to gravity affects them differently, it's that air resistance affects the way that acceleration due to gravity is able to act on them. So once we've got the idea that acceleration due to gravity affects all things equally, the next thing to do is to actually look at that projectile motion. So if I take this cube and I toss it up into the air, you should notice a couple of things. First off, when it leaves my hand, it leaves with a certain velocity. Let's just say 0.5 meters per second. But as it travels upward, eventually it comes to a momentary pause in its motion and then reverses direction and starts moving back downwards. The reason for this is that when I push this upwards or I toss this upwards, I've got a velocity in the positive y-axis or positive value. Acceleration due to gravity is always downwards or in a negative direction. So what's happening is that when this leaves my hand and starts moving upwards with that positive velocity, acceleration due to gravity acts to slow it down. In other words, that negative value. And as it slows it down, it's bringing that velocity from the 0.5 where it started up to or down to a velocity of 0. So it comes to a momentary pause, but just because the velocity has reached 0 does not mean that acceleration due to gravity stops. It's always acting downwards at 9.8 meters per second squared. So as soon as it brings that velocity to 0, it then reverses its course and starts accelerating it, still at 9.8 meters per second, back downwards, in which case now the velocity is going to go from 0 back to some value. And what we find is that that value of velocity, when it reaches that original height, is the velocity that it left that initial position as. So a couple of key points in this. First off, at the apex of a trajectory, the vertical velocity of the object always equals 0. And this is doesn't really matter, or it doesn't matter at all whether it's thrown directly upwards or if I toss this off to the side and it also has a component in that x direction. At that apex, the vertical velocity is going to be 0. Doesn't mean that the velocity in the x is 0, just the vertical, because along the x-axis, acceleration does not have an effect. So acceleration along that x is 0. That velocity stays constant. But along the y-axis, where I have acceleration due to gravity, I'm going to see that velocity go to 0. So again, regardless of whether I toss this up into the air, straight up and down, or I toss it at some angle, at that apex, it's going to have a vertical velocity that equals 0 meters per second. Another key point with this is that the time taken to reach the apex equals the time taken to return to the original height. And of course, this is when we neglect air resistance. Now, the reason for this, if we look at some equations real quickly. So we've got this equation that says acceleration equals a change in velocity over time. Well, again, let's assume this starts out with the velocity of 0.5 when it leaves my hand. That acceleration is 9.8 meters per second. And we can rearrange this equation to get that time equals a change in velocity over acceleration. So if my change in velocity is my final velocity minus initial, so final velocity at the apex 0, minus the initial velocity of 0.5, divided by acceleration, then I can calculate how long it takes to reach that apex. And that's going to be a key thing when we start talking about projectile motion, where you're launching this at an angle. And we look at problems in a future video. But the idea on this is that as it goes from 0.5 to 0, based on acceleration to gravity, it's going to take a certain amount of time. Well, that amount of time is going to be the same if I'm going from 0 back to 0.5, because this change in velocity can be set up as my final being 0, initial being 0.5, or my final being 0.5 when it returns, and the initial being 0. So in that, what we get, again, is the time taken to reach the apex equals the time taken to return to the original height. Okay? The other key point of this is that the velocity of the object when it returns to its original height is going to equal the initial velocity when it is first projected. The reason for that, take a look at another equation, is this one here. Okay? That says my final velocity squared minus my initial velocity squared is going to equal 2 times my change in y. So the idea is this. My acceleration is going to be constant. And if this goes up so far and then falls back to original height, then the delta y in each case on the way up and the way down is going to be the same, which means it has to equal this. So if I start out with, again, my velocity of 0.5 and a final velocity of 0, then I'm going to get a negative value. In this case, for this side of the equation, it's going to be a negative 0.25. But if I'm looking at moving downwards, then my final velocity is my 0.5, initial is the 0, and now I'm going to end up with a positive 0.25. So the same value for my overall change in velocity based on the fact that it's changing over the same distance. So what we end up getting is, again, this key point that the velocity of the object when it returns to its original position is going to equal the initial velocity as when it left. So to kind of visualize this all together, if this leaves at 0.5, then as it moves upward over a given increment of time, it's going to cover a certain distance. The velocity is also going to reach 0 at the apex. So I've got a certain distance that it's traveled. I've got a certain change in velocity, 0.5 to 0. My acceleration that's constant, and I can calculate how long it takes to go from 0.5 to a velocity of 0 over that distance. Well, if it now falls back to original height, then my distance is the same, the amount of time that it takes is the same, and as a result, the change in velocity is going to be the same. So again, those two key points, the time taken to reach the apex equals the time taken to return back to the original height. And the velocity of the object when it returns to the original height equals its initial velocity when it was first projected from that height. So two main key points there that are tied together and can be verified through equations. Now, where this gets a little tricky in some physics problems is that they'll tell you that it is launched from a certain height, goes to its apex, and then whenever it returns, it's caught some distance above its original launch point. In that case, we can look through this logically first before we turn to equations and say, okay, well, on the way up, let's say it takes 5 seconds to go from the initial velocity to a final velocity of 0. Covers a certain height. Well, if it's not falling as far, then it's not going to travel for as long of an increment of time. Because it doesn't travel for the same increment of time, it doesn't have enough, or that acceleration due to gravity acts over a shorter increment of time, and therefore we end up with a lower velocity when we catch it than the velocity had when it was launched. Conversely, if this is launched from a certain height and then caught below that original launch height, then we're going to find that its final velocity at a point below the original launch height is higher than what its initial velocity is, because now it's traveling for a longer period of time based on that acceleration. And again, if we look at that equation derived to a third one, we see that a change in velocity is always going to equal acceleration times time. So if it doesn't travel for as long of a period of time, then I don't get as large of a change in velocity. If it travels for a longer period of time, I get a longer change in velocity. So we can solve those out logically before we ever turn to the equations. The last key point on this is for objects launched at some angle. And this typically is the majority of type of projectile motion problems that you face in general physics as well as AP physics, college physics. Okay? Because upwards motion, the equations are pretty straightforward. Okay? Distance, time, acceleration, change in velocity. But when you launch it at an angle, you don't just have a velocity in the vertical, you also have a velocity in the horizontal. So when this is tossed from one hand to the other, and it leaves one hand at an angle, part of the velocity is in the vertical, part of the velocity is in the horizontal. And we have to use sine and cosine functions to determine what the individual velocities are. And they don't add up to the initial. If that initial velocity is 0.5 along that angle, say of 30 degrees, then to find the velocity in the y-axis, then I need to take the sine of that angle and then the hypotenuse of 0.5. To find the horizontal, I need to take the cosine of that angle and the hypotenuse, the 0.5. And I'm going to get two different values, and those values will not equal up to be 0.5. So don't just think that you can equally divide that velocity between the y-axis and the x-axis. That is not the way it works. You do have to use sine and cosine functions. But here's the nice thing. When you are launching it at some angle, the time taken to travel from that original height up to the apex and then back to the original height is the exact same amount of time that that object has to travel in that horizontal. So if it takes, say, 2 seconds to reach the apex, it's going to take another 2 seconds to go back to original height, like we discussed before. So I've got a total time of travel of 4 seconds. Well, if I know what that velocity in the x is, then I can take that velocity in the x and the time that's in the x-axis, and I can solve for how far away from the launch point that projectile is going to land. And that's the thing that ties together the x and the y-axis of projectile motion. The time in the y-axis, total time in the y-axis, to go from point of origin to the apex to the final resting position, where that resting position is at the same level, higher than, or less than. The time taken in that y-axis throughout that entire trajectory is the exact same amount of time that that object has to be able to move along the x-axis. So I want to show you a quick demonstration that projectile motion is independent, and the way that acceleration due to gravity works is independent of whether you have straight line motion or you have projectile motion. So I've got this apparatus, and what it has on it is this plunger system that I can set with a spring. And whenever I flip that switch, what happens is on one side this bar is retracted, on the other side this bar shoots outward. Okay? So then what I can do is I can set this, and I've got these two spheres. One of them has a little hole in it so that it can fit onto this side. The other one is solid, which brings up another point. This with the hole has a different mass from this one. But if I take them from the same height, and I drop them, they hit at the same time. So again, another example and verification that acceleration due to gravity does not care what the mass of the object is. It's always going to accelerate at the same rate. In my other tray, these don't bounce all over the place. And I'm going to set one up here so that it falls straight downwards, and this one on this platform, so that when the spring is released, it's going to project it outwards. So here's what we should expect to see. We should see when I flip this switch that this sphere drops straight downwards. This one is projected outwards. The fact that this has a horizontal velocity has absolutely no effect on acceleration due to gravity acting downwards. And as a result, they should still both hit the trays at the exact same time, just like they did when I held them up and I released them from the same height. It doesn't matter that this one is being projected outwards. So let's give that a shot. Sit on there properly. Sit on there. There we are. All right, in 3, 2, 1. Don't know if you could hear that, but they both hit at the same time. So let's do it again. Now you know kind of what to expect. It's on here again. It's on here. You should again hear them strike these at the exact same time. And we do. So again, what this means is that acceleration due to gravity, not only does it treat everything equally regardless of their mass, but it also treats everything equally regardless of whether it is in free fall, in other words, just falling straight downwards with no extra forces acting on it, or if it's put into projectile motion and has an additional x component of velocity. Acceleration doesn't care. Okay, so that is projectile motion. If you have any questions, please feel free to leave a comment for me and I'll get back to you. Also, don't forget to subscribe to this channel so that you can get updates whenever I put out new videos. And as always, if you have ideas for future videos, leave those in the comments as well. Hopefully all this has made sense. Take care.